We've all seen a digital character do this. The AI identifies a target behind an obstacle, it runs directly toward it, and then gets locked in an endless stutter and loop against a brick wall. This happens because the character is running on a greedy algorithm. At every single frame, the code calculates the immediate distance to the goal and takes the exact step that makes that numerical distance smaller. The logic is essentially nearsighted. It only sees the immediate mathematical benefit of the next step, leaving it blind to the larger layout of the environment. If the solution requires moving laterally or stepping away from the target to find an opening, the greedy algorithm simply doesn't know those paths exist. When an agent prioritizes direct, relentless pursuit without awareness of obstacles, it doesn't find a shortcut, it finds a fatal system lock. To navigate space, stop thinking in lines and start thinking in waves. This grid uses concentric expansion, exploring outward in all directions, like a water ripple. Expanding uniformly means wall complexity doesn't matter. When the wave touches the target, it guarantees the shortest path. Computer scientists translate this physical phenomenon into executable code using a framework called breadth-first search, or BFS. But to make a machine understand this organic ripple effect, developers build a highly rigid mathematical engine to govern every step of the expansion. The engine of BFS is a data structure called a queue. It operates on a first-in, first-out basis, meaning whichever coordinate is discovered first is the first one the computer processes. The loop begins by pushing our starting coordinate into the queue to establish the center of the ripple. Next, the engine removes that first item and branches out to evaluate all of its immediate neighboring coordinates. It then takes those newly discovered neighbors and pushes them to the back of the line to wait their turn. This loop forces the computer to completely process every location at distance 1 before it is allowed to evaluate any coordinate at distance 2. However, a raw BFS engine is prone to a catastrophic glitch. The program executes, but the character jitters erratically back and forth between two spaces. This happens because the algorithm steps to a neighbor, and that neighbor then looks back and adds the original tile back into the queue. This creates an infinite cycle. The queue size explodes exponentially as the computer tries to remember billions of redundant steps, eventually leading to a fatal out-of-memory crash. The architectural fix is the visited set, an independent memory bank that acts as the brakes for the engine. It records every tile the algorithm has already processed. By checking this set before adding a node to the queue, the code ensures it only visits each point, or vertex, and each connection, the edges, exactly once. This locks the time complexity to O of V plus E, ensuring the search stays efficient even on massive maps. Avoiding a system crash depends entirely on the algorithm's ability to maintain a strict historical record of its past actions. With the visited set in place, the AI is fixed. It smoothly navigates around the original brick wall without stalling or looping. We can scale this further using multi-source DFS. Instead of starting with one point, we drop multiple starting coordinates into the queue at the very beginning. These ripples expand outward simultaneously, mapping vast territory until their boundaries collide. This computes the shortest distance from every point to its nearest source in one pass, transforming the search into a topographical map. Algorithmic problem solving shows us that making optimal progress requires a balance, systematic exploration of the unknown, and an infallible memory of where you have already been.